All right, here we go. All right, so let's start by listening. All right. Okay. Quiet, paying attention. All right, so just to recap really quickly about what we have done so far. Okay, so what we have done so far, if we wanted to find the area between curves on a segment like A to B, we would do the integral from A to B of f of x minus g of x dx, where this is my top function and this is my bottom function. Okay? Now, there is something weird about example 1 on this. What is different about that question versus other ones we've seen so far? Okay, it's in terms of y, right? It's an x equals equation. It's in terms of y. So, Desmos comes in handy here. To graph that on your calculator, you have to solve them for y because your calculator will only graph things solved for y. But Desmos comes in handy for us to picture what's happening here. Because Desmos will graph things that are in terms of y. So if I graph this here, you can see the picture of what we're looking at. Okay? So normally we've been doing top minus bottom, right? Okay, so that will work fine for part of this, but what happens when we get past 2 right here? Because we're looking at this area right here. What's our top function? Red or blue? Red. What's the bottom function? Red. It's itself, right? There is a way you could do this with y's because you would have to solve this. It's going to be like plus or minus square root of x sort of stuff. There's a way you can do it like we have done it, but it's not going to be the easiest way to approach this problem. The easiest way to approach this problem is to just keep it in terms of y. Okay? So, I'm going to export this so we can put it over here and draw on it. Let's go back to full screen over here. Let's make this small enough so we can deal with it. Alright, so you obviously won't have Desmos on a problem like this. They will probably either give you pretty simple ones that you can graph, or they'll give you a picture on these types of problems. Or it could be calculator active. Well, actually, calculator active does not help you as much on these because you would have to solve them for y graphing. So the best way to deal with this is to do the same problem, but in terms of y. So whenever you are doing this problem in terms of y, okay, what you're going to do is you are going to do, I'm going to call this, I'm going to do the integral, I'm going to call it C to D instead of A to B. These are going to be limits from the y-axis. And we are going to integrate right minus left with respect to y. Okay, and so these limits right here do not come from our x-axis, they come from the y-axis. Now, we have a problem trying to do top minus bottom here because we don't have a function that's always the top function, and we run into this. But when we are thinking about right and left, do we have a function that is always to the right and one that's always to the left? We do here, right? The red function is always to the right, the blue is always to the left. So that works out well for us. Now, if we were not doing this with a calculator, or if they did not give us a graph, we would need to know our intersection points. To find those intersection points, we can set these equal to each other. They are both equal to x, so we can set them equal to each other, 3 minus y squared equals y plus 1. And so I would move everything to one side. Here, we're just adding that y squared and subtracting that 3 to get y squared plus y minus 2. And then if we factor that, we'll have y plus 2, y minus 1, and that will give us y equals negative 2 and y equals positive 1. And if you look at our graph that we have over here, this intersection point, its y coordinate is negative 2, and this intersection point, its y coordinate is positive 1. So those are our intersection points that we have here. So to set this up, we would do the integral from negative 2 to positive 1. Notice I'm pulling those. I'm thinking of my y-axis here, negative 2 to positive 1. I'm not thinking about the x coordinates here. I'm thinking about the y coordinates because everything's in terms of y. And then we would have our right function, which is the red one, which is 3 minus y squared, minus our blue function, which is on the left, which is y plus 1. And we would put a dy over here because we're integrating in terms of y. Everybody okay here? All right, so if we simplify that, actually, okay, if we simplify it, we are going to get negative y squared. That'll be minus. That'll be minus. So we'll get minus y plus 2 dy. And it's likely you'll see this on a calculator inactive problem, but I feel confident in your ability to integrate that and evaluate it, and we don't have a lot of time today. So let's integrate it on the calculator. Negative y to the second minus y plus 2, comma y, comma, negative 2, comma, 1. No, what have I done wrong? Oh, I put a T somewhere. Look, I just put a T in the middle of that for no good reason at all. I think T, I hit T instead of a comma, didn't I? 9/2. Now, there's no reason we need to do that on the calculator other than time right now. And a lot of times for a lot of these problems, because they are a little bit lengthy to work out, sometimes, especially when you see these on free response, they won't ask you to solve it. They'll just say, set up, but do not solve, and ask you to do this, or it might be on calculator active. So, so it's not uncommon to either do this with a calculator or just only set it up for that. Okay, let's look at another problem. All right, find the area of the region bounded by the graphs of y equals x to the third, x equals 4y, and y equals 0 and y equals 2. Let's try to do this one without graphing it, or well, without looking at the Desmos graph, because sometimes you'll see these without a picture. So I see what I like to look at first is I've got y equals 0 and y equals 2. That sort of helps me know what I want to make my window look like, because I know I'm going to be looking at those horizontal lines at 0 and 2. Those are sort of like our limits that we're going to be using. And so if I think about plugging in 0 and 2 to this one, I'll get 0 and 8. If I plug in 0 and 2 here, I'll get 0 and 8, right? So those are probably also going to be my intersection points. So if I'm graphing this on my x-axis, I need to go from 0 to 8. On my y-axis, I really only need to go up to 2. And so if I just graph my points, y to the third, so 0 to the third is 0. 1 to the third is 1. And 2 to the third is 8. but remember, like, the 2 that we're plugging in is your y coordinate. So it's not the 0.28, it's 0.82. So, you know, if you're thinking about what a cubic looks to, this is just like a cubic on its side. You've got this graph here. That's our green graph. We're going to have, I'm going to go ahead and draw in, we're going to have horizontal lines here. And then let's use red for this. Sometimes the easiest way to do this, because my mind gets, well, you could do it a couple ways. Sometimes it's best just to plug in some numbers. Like if I plug in 0, I get 0. If I plug in 1, I get 4. So that's the 0.41. And if I plug in 2 for my y, I get 8. So that's going to be this point right here. So sometimes just plugging in numbers might be your best bet. Or you could solve this for y. It's going to be y equals 1/4 x. So you got a slope of up 1 over 4 if you think of graphing it in terms of x. So the main thing we need to do here is know what is our right equation and what is our left equation. Which one is to the right here? Red. Green will be to the left. They actually didn't even have to tell us y equals 0 and y equals 2 because those end up being the intersection points. But the fact that they did makes this a little bit easier to kind of get your picture right. So if we want to set this up, what are our limits of integration? 0 to 2, not 0 to 8, because we're doing this in terms of y. So we are looking at that y-axis. Whenever these problems get mixed together with problems that are in terms of x, sometimes it's easy to mess that up, right? But because we're doing this with our equation solve for x, we have a y here. We now look at our y-axis for our limits. And so we are doing the right-hand function, which is 4y, minus the left-hand function, which is y to the third. I'll put a dy here. And again, that one's not difficult to do by hand, but for the sake of time, we're still going to just do it over here. I don't know. I might could do it faster without the calculator, but probably not. And we get 4 for that. It's the same idea as we were doing with the area between curves with respect to the x-axis. You just kind of have to turn everything sideways whenever you're thinking about it. All right, let's look at this problem. This one is not immediately obvious that you need to use a y. So let's think about the graph of this. We got x equals 0, which is our y-axis. We got y equals 1, y equals 3. So if I think about graphing this, I think we only really need first quadrant here. So on my y-axis, I'm going to have y equals 1. I'm going to have y equals 2, or 3, and I'll have x equals 0, which is the y-axis itself. So let me color code this. Okay, so 3 over x, if I start plugging in, some numbers, I've got 3 over 0 would be undefined, right? No, I can't plug that in. If I plug in 1, 3 over 1 would be 3. So 3 over 1 would be 3, so that would be 1, 3. Right? We're plugging in an x, so our x is 1, our y would be 3. If I plug in 2, I'm going to get 3 halves, which is 1.5, which will be about right here. If if I plug in 3, I get 3 over 3, which is 1. So 3, 1 would be right here. So, and if you kind of remember what these look like, you're going to have an asymptote right there. So our area that we're looking at is right here. Okay, so you do not have to do this problem in terms of y. You can do this problem in terms of y, and I would argue that it might be easier to do it in terms of y. But you don't have to. Because we can use this in terms of x's, but we're going to have to break it up. Because right here, if we do this in terms of x, what's top function here? What color? If we're looking just from 0 to 1, what function's on top of our bounded region? It's going to be that red function, right? That's our top boundary. Yes, blue is above it, but it's not the boundary of our region, right? So what we really have right here, if we try to do this top minus bottom, is we've got like this rectangle right here, right? Top is 3, bottom is 1. We could actually just find the area of that rectangle, which is going to be 2, right? And then we would have to do our integral from 1 to 3 of top minus bottom. The top would be the blue, which is 3 over x minus 1 dx. Okay, so it can be done this way. But I would argue that it is easier, particularly if you're having to evaluate it without a calculator. I think it is easier to do this problem in terms of y. Okay? Because if I look at this function and I'm not thinking top minus bottom, oh, I didn't mean to do that. If I'm not thinking top minus bottom, if I'm thinking right minus left, what function is always to the right? The 3 over the x, the blue function, right? What function is always to the left? X equals 0. Okay? So now if I'm going to do this, I've got to take this function, y equals 3 over x, and I have to solve it for y and for x. So I would multiply both sides by x. So xy would equal 3. And I would divide by y. See, it ends up being like basically the same equation right here. X equals 3 over y. So that is this blue function here. I can either call it y equals 3 over x, or I can call it x equals 3 over y. They're both the same. And so if I want to do this in terms of y, I could integrate, what would my limits be? 1 to 3. I'm pulling those from my y-axis here. 1, 2, 3 of 3 over y minus, I'm going to write it right here, but we're going to take it away immediately. This right here is x equals 0. So 0. Is that really necessary right there? It is not, because it's not going to change anything. So I'm integrating just 1 to 3 of 3 over y dy. Let's actually do this one by hand. What do I get when I integrate that? 3 natural log of the absolute value of y, and I will evaluate that from 1 to 3. And so I'll get 3 natural log of 3 minus 3 natural log of 1. What is natural log of 1? 0. So 3 natural log of 3 is going to be my answer. Now, just to make sure, let's go up here. We're going to just use the calculator for the sake of time. Let's make sure we get the same thing. If we do it in terms of x, 2 plus the integral of 3 over x minus 1 comma, x, comma, 1, comma, 3. Ugh. Close my 3 natural log 3. Yeah, so same thing. It can be done either way. There's not going to be anything telling you you have to do it in terms of y. But if you notice that it's easier that way, that will help you. Okay, questions on that part? All right, let me see if I want to do this. I think we might be able to skip that one for now. Let's go to the other set of notes. All right, so we're going to use our calculator quite a bit on this one as well because it's really mostly about being able to set it up, not as much about being able to solve it. I'm also okay if you use your calculator to solve some on the homework. Just make sure that you are writing down your setup on everything. All right, so area of the region between this cubic and this quadratic. Very similar to what we did for the warm-up, right? They give you this picture right here that shows you your intersection points. It also is going to make it pretty clear which function is on top. This function here is going to be your cubic because it has 2 turning points. This one is your quadratic. If we want to set this up, and let's say this was a calculator active problem on the FRQ. If I want to set this up, I need 2 separate sections. Am I going to do this in terms of x or in terms of y? Definitely x for this one. Your equations are in terms of x. Top minus bottom is much easier to think of than left minus right on this. It could be done, but it would, well, I don't know if it could be done. I don't know if you can get these equations in terms of y. That'd be terrible. I'm not saying it can't be done, but it would be terrible if you tried to do it in terms of y. So we are going to do top minus bottom, and we're going to start with this first section. So for this first section, our limits of integration are going to be -2 to 0. We're pulling those from the x-axis because we're in terms of x. And our cubic is on top. The cubic is f of x. So we'll do f of x minus g of x. And I would encourage you, if it is calculator active on a free response problem, do not write this whole expression out. Just call it f of x and g of x. It saves you time. It also keeps you from making a mistake by forgetting a negative or something like that. Okay? So we're just going to do -2 to 0, f of x minus g of x. Then from 0 to 2, they're going to switch. So we'll have g of x minus f of x dx. And we are going to use our calculator to evaluate this. And if it's on a calculator active problem, you definitely have to write this down. Don't leave that part right there out. You need to write that down because you have to write down what you're putting into the calculator. But from this point, you can do the whole thing in the calculator. So, oh wait, you can't do it till you put your functions in y1 and y2. So 3x to the third minus x to the second minus 10x and negative x to the second plus 2x. And so, I didn't really mean to graph that. We don't need the graph because it's already been given to us. Wasting time here. Okay. y1 of x minus y2 of x, comma, x, comma, -2, comma, 0, plus our integral of y. 2 of x minus y1 of x it should be, but I have a negative right there. Yeah, negative 2 comma 0 is what you should have. Comma x, comma 0, comma 2. Let's hope I've typed everything in right. Come on, 24. This is one that could be done without a calculator. It's just going to be intensive if you do, because you got quite a bit to integrate there. Okay, questions? All right, I think this is a kind of cool problem right here. It is old because our book, well, actually this came from the textbook we had before that, which is the same textbook, but they've like significantly updated it. It's old because it's talking like 1960 to 79 and then 79 through 93, so like that probably seems ancient to you guys, but it's still a pretty good problem. So petroleum consumption patterns have changed in recent years. The rate of consumption in billions of barrels per year of petroleum in the United States from 1960 to 79 is modeled by this equation. This is your rate right here. And then from 1970 to 79 through 93, the rate of consumption is modeled by this cubic function. So if we want to find the total amount of fuel saved, what would we need to do is it asking here? And we're looking total amount of fuel saved since 1979. So this would be calculator active. So the first thing we would want to do is put our equations in the calculator. So if we go to y equals, we can type these in. And we're going to have 0.18. I'm going to use an x instead of a t. Negative 0.002. Hopefully I've got that in right. All right, so this is a really good place to use Zoom Fit because we know that we're going from negative 10 up to 23. Really, 9 to 23 is what we care about, but it might be helpful to see both. So negative 10 to 23. So I'm going to go to my window, and I'm going to put in negative 10 to 23. And I'm going to make sure you hit enter after that. So go to your window. You know your x values need to be negative 10 to 23 just based on the parameters of the equation given to you. And you're going to graph that. And you may or may not see much of anything. It might show up pretty good actually. Okay, you've got a pretty good graph right here. So I would just stick with what you've got. But if the graph does not show up well, you could always do Zoom Fit for that. This is going to be pretty good because we really only care about since 1979. So that would be at x equals 9 there. So you were using this linear function, but it switched to this cubic function. So if we are wanting to know the total amount of fuel used, these are both rates, we would find the area underneath that curve, right? So the total amount of fuel used underneath that line would just be our integral. And if we want to know the amount saved, we're looking at the difference in those two areas. So that's going to be the difference between these areas right